All right, guys. So just like I was saying today, let's just do some, keep working on the problem 441 that we started the other day, but you're gonna have to do the calculations for me because every time you open this problem here, you get different data, okay? But the procedure should be the same. So I won't be able to check over here the results. So you're gonna have to help me on that one. All right. So the other day we started doing problems out of the homework, and the first one we did was 441. Where basically there's a compressor, all right, and they ask you to calculate what is the volumetric flow rate at the exit of the compressor given the data, and then you know a compressor is going to require work in order to operate. No, you want to compress something, you need to provide power to the compressor. So basically what I want to do is to know how much power you need to provide to the compressor in order to have these things to happen over here. All right. So we did the first part and we find out that the volumetric flow rates had to be 0.0299 cubic meters per second. All right. So now in order to do the second part, which is today, so this will be lecture 16. With the problem 441 continuation. We need to do part B, which is to determine the power required to operate the compressor. So power, okay, for the compressor. So in order to do that, what I'm going to do is, again, I'm going to redo the figure. So we have the figure of the compressor over here. All right. And we know that in order to operate the compressor, you need to provide power to it. Okay. So this will be our system over here. This is what I'm doing this. This should be our control volume. And we know that within our control volume, let's see, what do we have? We know the substance is refrigerant 134A that initially is saturated vapor at a temperature of minus 26 degrees Celsius. P2 is 8 bar at a temperature of 70 degrees Celsius. Okay? And they tell you that the system is insulated, so you know the heat transfer is 0. Okay. So what do we need to do over here? What type of system is this? This is a control volume system. Okay? So we need to apply the first law, the first principle of thermodynamics for a control volume system, which will be what? Q dot minus power. In this case, what are we going to have? Plus M mass flow. We know this conservation of mass flow is steady state, so M1 equal M2. We did that on the previous problem. So it will be M. What is coming in? H1. Then we neglect kinetic and potential energy, and what will be coming out? M dot H2. Okay? So over here, we know that the system is insulated, meaning that it will be no heat transfer. And basically from here, you can get the equation that the power required for the compressor to operate will be M dot of H1 minus H2. Okay, so we're gonna calculate the value for m dot, but we have all the data over here. So let's maybe calculate it now, where m will be equal to AV1 divided by V1. So you want over here, we can say where, so we need your help, where m mass flow is equal to AV1 divided by the specific volume 1, which we know is equal to what? AV1 is equal to 0.18 cubic meters per second. And V1, it was found from table 810E to be equal to 0.1882. 0.1882 kilograms per cubic meters per kilogram. So this is going to give us, what do you get for M? So it's probably going to be about 1, no? A little lower than 1. What do you get if you do this? 0.18 divided by 0.1882. 0.956, and the units for this should be equal to what? Kilograms per second. Okay? So basically, we know what the mass flow is, and now we need to find the values for H1 and H2. Okay? So for H1, again, we're going to have to go to the tables. So what do we know as state 1? Do we know two things? We know that the state is saturated vapor, and we know the temperature, no? Okay? So state 1 will be saturated vapor. T equal to negative 26 degrees Celsius. So I think we need to go to table 810. We can do that now. At T equal negative 26 degrees Celsius, we're going to have that H1 is going to be equal to H sub gas, all right, because it's the saturated vapor, no? Okay, so if we do that, I like this one here. So let's see, table 810, 6, 9, pass it 810 at basically minus 26 right here. H1 will be 214.8, no? Yeah, so 214, no, this is HFG, so this will be 231.62. So 231.62, and this should be kilojoules per kilogram. All right, so that's what I put over here. And for H2, we also need to know two things. So we know two things for H2. We know the pressure, we know the temperature, no? So you know two quantities, you can go to the table. So T2 equals 8 and T2 equals 70. Okay, this is from the previous problem, on the previous section. What do we have? You see that here we had to go to, it's superheated, so we needed to go to table 812. All right, so we go to table 812. And what I have over here is table 812. Again, H2 will be equal to over here, 812 at 8 bars. 7, 8, and the temperature of 70. So 8 and 70. You have H will be equal to 305.5. Okay, so 305.5 kilojoules per kilogram. So basically now we have all the information that we need in order to do the numerical application. So we can say, so finally, the power equal to m dot h1 minus h2 will be equal to what? Will be equal to 0.956 times, the units are good, kilograms per second. This is kilojoules per kilogram. So we ended up having kilojoules per second, which is a what, no? So this will give you minus H1. So H1 we find out to be equal to 231.62 minus 305.5. And this is kilojoules. So the result you get here will be in kilowatts. $70.6. Okay, let's see here. M, let's see if I did here a mistake. M, I move this one to the other side, would be H1 minus H2. Okay, yeah, that is correct. So why is that correct? I was just thinking about the sign. If you remember, what is the sign convention what is the sign convention we're using? Is heat going in is positive, no? Yeah. But the work, if you need to do work inside on the system, it will be negative, no? So you see, in order to operate the compressor, you need to provide a power of 70.6. Okay. So I don't know on the problem if there were, yeah, you see the problem here is that they just give you the magnitude, but really should be a negative sign, no? So be careful when you solve. Maybe I would have put the minus sign, but here it looks like they just ask you for the magnitude. Okay. Anyway. So, okay, here we are on the assignment. Which one you want to do over here? I think the first one, when I look at it, was a good problem. I mean, you choose this one, this one. This one looks about the same. This one. I mean, as soon as you see one that you like, let me know. You want to do one of the difficult ones, maybe these ones, and see what happens. So 476 or 471. You want to work with turbines or with compressors? 76 is fine.
So on a test, with the work of the last question we just did, the data sign would be part of the answer.
I mean, on the test, I don't know. The test will be whatever you put on your page.
Right.
But what I'm saying on the homework, I would have put a negative value, but it looks like they just wanted the magnitude. Okay? Because it's really negative. What happened is that they say W in, no? So that's specific. So. All right, so this is supposed to be page 84. All right, so hopefully as soon as I open that one, we'll have the result for the proper data and we're able to finish it. So you want to do this problem then, 476. So just do the figure. I will do the figure on my page as well. Okay, so just do the figure. So it looks like separate stream of steam and air flow through the turbine and heat exchanger arrangement shown in the figure below. And they give you a bunch of data that hopefully everything is on the figure. M5 is on the figure, no. So M5 is 2000 and work turbine 1 is 8000. Steady state operation, I'll provide it. Okay, I'll just do the figure. That will one turbine here. Let me do another turbine over here. All right. So a turbine gives power. So the same thing, the compressor, you need to, so it's 8000 kilowatts. Okay, the second one is unknown. On one side, we're gonna have steam. Steam at 1. You know T1 is equal to 600 degrees Celsius. T1 is equal to 20 bar. Then all this is gonna go into a heat exchanger. Okay. We have steam at 2. You know T2 would be 400. T3 is 10. And now this is going to the other turbine at 3. And you know that T3 is equal to 10. T3 is unknown. And then exit at 4. T4 equal to 40 Celsius and T4 equal to 1 bar. Okay, so that's for the steam or the water. Then on the lower part of the heat exchanger, you're gonna have looks like it's like air, so at 5, air, and it would be T5 equal to 1500 Kelvin, T5 equal to 1.35 bars, and at 6, T6 equal 1200 Kelvin, and T6 equal to 1 bar. Okay, so in the data, they give us the work turbine 1, and they give us M5, the mass flow of the air to be equal to 2000 kilograms per minute. Steady state, heat transfer with the surrounding can be neglected. So basically you see that Q is 0. As all kinetic and potential energy can also be neglected. And what do we need to do? We need to find the temperature T3. In Kelvin and the power output of the second turbine. Okay? Okay. All right. right? So let me go to my page over here. This is what I've done over here. This is my figure. The first thing we need to do is to find T3. Okay, so again, let's see how we can do this. So my initial guess would be, it looks like we know everything at 2, at 6, at 5. The only thing we need something is at 3, no? Okay, so my initial intuition would be to take the heat exchanger as our control volume. Okay, so for the below control volume, basically will be the heat exchanger. What do you have? Here your two, 3, 5, and 6. Okay, we have the data here on top. But if you want, let's put it here. We have T3 equal to 10. T3 equal to question mark. T5 1.35. T5 1500. T6 1. T6 1200 Kelvin. This is Kelvin and bars. And T2 we have 10 and 400. I'm not wrong. Okay, check my data. Okay, so this is important part on an exam or anything. I want to see what is the control volume. So for this control volume over here, so this is for your control volume 1. Let's say for control volume 1, we're going to apply again the first principle of thermodynamics equation for this equation. So what would we have over here? You have Q dot minus power plus what? This would be what? M of the water. So let me say MW dot, then H2 is coming in. What else is coming in? Plus the mass flow of the air, no? Which is the green one. So M5, H5. So this is coming in, no? Going this way, and this is coming in. Now, what is coming out? Will be the mass flow of the water times H3 plus the mass flow of the air. Oh, this is M5. Let's call this one. I mean, you can go, you want to call, let's call this one N sub A, N sub A, and this will be H6. Okay? So everything's come from the figure. Is it any heat on that figure? No, it's insulated, no? Does the heat exchanger requires any work, any power? No. So basically from this equation here, we're gonna get what? What we need to solve is for H3. So if you want, you can write down, let's see, mass flow of air will be H5 minus H6. I'm moving to the other side, plus mass flow of water H2 will be equal to the mass flow of water H3 so that from here I can just solve for H3 will be equal to what? H2 plus mass flow of air. Oh, we need to solve for the mass flow of water. Okay. Sorry, for the mass flow of air first. This one here will be H2, H5 minus H6. Okay, so in this equation, what do we know? We know the mass flow of water, the mass flow of air will be equal to M5, okay, M dot 5, which is 2,000 kilograms per minute. I don't know if we're going to need or not, but can you do this one divided by 60 in order to find it in seconds? How much would that be in kilograms per second? 33.333, okay, kilograms per second. Oh, we're gonna have to find the mass flow of the water, but let's first try to find the other quantities, okay? Will be a bit easier. So we know this one. The next thing we need to do is to find H2. So can we find H2? Do we know two things for H2? We know the temperature, we know the pressure, no? Okay, so for H2, we know that the temperature at T2 equal 400 and P2 equal to 10. So let's see, and so what is the table we need to use over here? So probably it's table A2, A3, one of those ones. I mean, I could go, since we have this, what is this table? 6, I could just go and look at the values. Let's do maybe the first ones together. So let's see, let's look at the pressure 10, see if I have it in bars. In A2, the system, or A3. Is the temperature in bars here? Yeah, so for 10 bars, what is the minimum temperature? Saturation temperature is 179.9, no? So really, what is the state at point 2? It should be superheated, no? Yeah? So then that means we need to go to table A4 at 10. Table A4 at 10, and at 400, we're going to get H to be equal to 3,263.9. Okay? So from table A4, we get that H2 is going to be equal to 10, okay, this one here, 3,263.9 kilojoules per kilogram. Okay? All right, that was table A4. So we got this one over here. Now, obviously we cannot find H3 because this is what we need, what's what we're trying to find. But we can do the same thing for positions 5 and 6, no? All right, so let's see at 5. Hopefully they have the tables. We don't have to do the assumption of the ideal gas. So H5. I don't know if they're doing the ideal gas assumption. H5, we know two things. We know at P equal 1.35 and T equals 1500. Okay, so let me go back over here. Maybe just look very quick, see if they did the assumption of the ideal gas. That way we save some time. Blah, 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 blah. So this is whatever that is. Now this is for the other thing. They did it the other way. So M2, M1. Okay, they don't say from where they got those values. So I guess they all come from tables. Okay. Okay, so I guess they use the tables for these ones. H5, H6. Okay, so I guess, all right. So they did not do the assumption, so let's go to the book. Here, so for air, I don't know which one is these tables for air, but I think it's at the end, like 8, what is it, 820, something like that? 22, so let's go to table 22 here. So this is air, we need to look for air. Hopefully we don't have to interpolate. I don't feel like doing it. So 820, this is for the CP value, so this is not what we need. 821, this is not what we need. 822 for the ideal gas. So assume here basically the pressures are what, 1.35. So let's just look at the temperatures. I don't think it's 23. Yeah, okay. So table 822, temperatures are in Kelvin. So what would be the temperature at T5 was 1500 Celsius, no? Don't tell me. Yeah, but I mean, I think this one was this temperature in Celsius or Kelvin? Oh, Kelvin, good. That's good then. So we have to, so 1500 Kelvin. I guess it goes here, the 1500. We get a value of H of 1635.97. Okay, so from table for H5, table 822. You find that H5 is 1635.97. Okay, and we do the same thing for H6. So at H6, we know P6 equal to 1, T6 equal to 1200. What's going to happen from table A22, H6, approximately equal to, so 1200 will be 1277.79. Okay, let me check something here quick. I think that's the same value that I have over here. Okay. Okay, so we can save some time with the calculation. All right. Okay. So now we have everything over here. on this problem, but now what we are missing is the mass flow of the water. Okay? We're missing the M dot W, this one over here. So in order to do that, the easiest way you could do, no, this one would be, you could do it from here, redo everything, but it's going to be easier if you just look at the turbine one. Okay? So if we look at the turbine one, so let's say for the below control volume, and this time we'll have your first turbine here. So this will be 1. This is 2. What do we know? T2 equal 400. T2 equal to 10. T1 equal to 600. T1 equal to 20. So for this control volume over here now, we're going to do the same thing. And we know that this turbine gives a power of 8,000 kilowatts. Okay? So if we apply the first principle of thermodynamics to this control volume, what do we get? So it's the same equation, Q dot minus power turbine 1 plus what? M of the water H1 is coming in, will be equal to the mass flow of the water coming out. Okay? So this system is insulated. So what does that mean? The Q is equal to 0, but this W now is not 0, no, because the turbine requires, the turbine gives power. So from here we can find what? We can find that, if you want, let's do that in 2 steps. Power will be equal to M dot water H1 minus H2. Or from here we can get that the mass flow of the water would be equal to H1 minus H2 divided by the power of the turbine 1. So let's see, this one, get one, H1 and H2. So I know we already have, we have H2, but we not calculated H1 yet, no? Oh wait, maybe I went too fast. Yes, I went here too fast. Sorry for that. So you're absolutely right. So this will be equal to the power of the turbine 1 divided by H1 minus H2. Okay? So over here, I was just one step ahead. We know H2, we know the work of the turbine. We don't know H1, no? But can we find H1 as we did for the other ones? You can just go to the table. So for the steam, so for that equation here, so this should be page 86. So over here, we know that the work of the turbine is 8,000 kilowatts. We know that H2, we just calculated to be equal to 3,263.9. And what we need is H1. So for H1, again, what do we know? We know two things at H1. We know that T1 equals 600 Celsius, P1 equal to 20. I think was bars. So this is for the steam. So again, we need to go to table whatever, we find out. A3, A4. Let me go up here for a while. Okay, so let's see table A3. This will be the pressure for, we know at P20, the temperature is 224, and here we have 600. So that means that this is steam, no? Superheated. So if it's superheated, we go to table A4 at 20. At 20, which column are we looking for? The before last, okay? So at 20 and a temperature of 600. So we get a value of 3,690.1. So table A4, we find that H1 is 3,690.1. Okay, so basically now we have everything. So substituting into the expression of mass flow of water equal to power turbine 1, H1 minus H2. What do we get? We're going to get so 8,000. And then we're going to get here H1 is 3,690.1 minus 3,263.9. So what do you find for this? 18.77. Okay, we can go check now. And what should be the units? This should be, this is what is kilojoules per second, no? This is kilojoules per kilogram. So it becomes kilograms per second. Okay, and if you want, we can go check with the solution since I have them. We'll save some time. So that's not what I want to do. So I guess it's here. See solution. Wait, oh, this is a different value, okay? So the turbine is 10,000. Okay, so we're probably correct. We cannot check the values. All right, so we check for T3, okay? So now that we have all these expressions, what can we do? We can go back to this equation. Now that we have all the values, we can go back to this equation. Okay? So now going back to the equation H3 equal to H2 plus mass flow of air divided by mass flow of water, H5 minus H6. Now we can just go and substitute the values. Okay? So what do we have for H2? H2 we had 3,263.9 plus mass flow of air. We just calculated that to be, no, we had that one before. In kilogram per second, I asked you to give me, that was the one you told me was 33.333, no? Yeah? Let's do 33.333 divided by 18.77. H5, we had 1,635.97 minus H6, which is 1,277.79. So what did you get for H3 then? And this should be in kilojoules per kilogram. So you do a calculation, what do you get? Okay, so some of you did the calculations, and we agree that we get H3 equal to 3,899.92. Okay, so now let's not forget. I mean, we've been going a long way for this problem. What do we need to solve for? T3, no? So now, do we know two things about T3? We know the pressure and we know the enthalpy. Okay, and we know it's steam. So let's say this is not going to be the fun part. So page 88. Let's see if I can move this one to the right. Page 88. So at 3, what do we know? We know that P3 is 10 bars, and we know that H3, we just calculated, is equal to 3,899.92. Okay, we need to find T3. Okay, so how do we find T3? If we know two things, we're gonna have to go to the tables and kind of interpolate, no? Not gonna be that fun. So let's go here and see what happened. Let's first look at this one over here, table A4, and see really what we have. So let's go to the other one. Let's see what we have over here. Pressure, okay, table A3, we go to 10 bars. Here we go. Which one are the value for the H fluid, H gas? So what is H gas at 10? 2,778.1, no? So what is the state of the water at point 3? Superheated. So this is not going to be fun to interpolate. So over here we go at 10 bars. So we have the value of what? 3,899. Is it there?
It doesn't go high enough.
Doesn't go high enough. So awesome. So probably that means that they ask you to do linear interpolation. But let's try. I mean, that's all we can do, no? So, okay, that's one of these fun problems, I guess. $3,899. So let's see how can I do this if they don't give us the value. All right, let's do it. Okay, I think I know what to do, but all right. So what I have in mind to do basically is, let me sketch it. Might be easier to visualize. What we try to find is T, no? Yeah. And we know the H. So what I'm going to try to do is assume a linear interpolation. Correct? So what I need to find is the slope of this line, no? Yeah? Okay. So let's say I first look at one point and then I'll do it directly. It might be easier. Let's just put it down. So at 10, let's take 2 points. So let's take 600 and 640. Okay. And let's write down the values for the H. So it will be 3,697. So From table A4, I get at T equals 600, at T equals 640, I get H, so this would be TA, B, HA. So I get HA of 3,697.9, and they want to have 3,787.2. Okay, check my values, but yeah, I'm correct. And this will be, you want the point. Okay, so from this equation, I'm going to try to find the slope. Okay, so what will be the slope? Let's say below M is generally just the tangent, no? How much it goes up, so how much it goes high. So how much it goes up over here, so what will be the tangent? Will be is positive, so will be 640 minus 600, no? Divided by 3,787.2 minus 3,697.9. So the form of the equation of this line is of the form y equal mx plus, let's say, whatever, b, no? Just trying to find the slope over here. So what do you get for the slope? I give you some time, so hold on. Let me pause. Okay, so now we know what? We know the h for us. So this is h sub d. So our h sub 3 here is 3,899.92. This is our h sub d, which is the 3,787.2. And this is the T here is 640. We're trying to find T3 over here, no? So if I use this, T3 will be equal to what? From the figure will be 640, okay? Plus what? The slope that we just calculated. So 0.449. And now, what is the space between this and this? So the x would be H3, which is 3,899.92 minus 3,787.2. And the 640 here is Celsius, or is it Kelvin?
You should check.
Yeah, I mean, I don't know. We will check. Is Celsius. So then be careful, because this one you need to transform everything into Kelvin, no? So you just have to add at the end 273, no? So what are you getting here in Celsius? You do this calculation. So if you do this calculation, you had how much? 690? 690 point something? Or just 690?
Like 26, that's what I, yeah, that's what I got.
690.26.
Six, just six.
Okay, so that's it. So Celsius. So now in Kelvin would be T3 would be 690 plus 273. Then is 273.2, no? But I mean, then I use 273. The problem is the accuracy. So this will give you the 900 and this should give you the 900 and 62.2, no? So that gives you actually what? 963.2, no? Not 62. If you do this calculation, you get what? 800 plus 163.2. So really I get 963.2 over here. So I don't know. I mean, I don't get the exactly, so be careful with the slope. Maybe it was the round off of the slope.
I think you're still within the tolerance.
Still within the tolerance? Good then, okay? Just want to say that I think it's ridiculous to have a 2% tolerance for this type of problem. But when I put this one, I always select the highest one, but I think other problems do not have the same tolerance. So let's do the recording, and that's just part A. Okay, awesome. So we did part A, part B. So part A was long, part B probably, hopefully it's not that long. We need to determine the power output of the second turbine. So that's going to be easy. Okay. Once we have all this information, okay, so this is doing the interpolation from table A4. And now, part B, we need to find what is the power provided by the second turbine. Okay, so now that we have all the information, this is going to be pretty straightforward because what do we need to do? This time we need to consider only as our control volume the second turbine. Okay, so for the below control volume, which will be turbine 2, we have 3, 4, and we need to find is what is the power provided by this turbine. We know H3, so we know P3 is equal to 10. No, wait, we're gonna have to interpolate again to find the H. T3 is equal to, we just find out 963.2. All right, and what else do we know? T4 is 240, and T4 is 1 bar. Okay, so for control volume 3, we can write down Q dot minus power turbine 2 plus M water H3 will be equal to mass flow of water H4. Once again, we know this is an insulated system, so we have power, the heat is 0. So you're going to get that the power provided by that turbine should be equal to the mass flow of the water, H3 minus H4. So in this problem, we know what the mass flow of the water is. So we know mass flow of the water. What was it? We can find it. Is 18.77. Okay. The H3, no, H3 we don't know. H4, okay, we need to find H4 and H3.
We know it's true.
Do we know H3?
Yeah.
Ah, okay, awesome. H3, yeah, that's how we find it. It's true. H3 is 3,899.92. Okay, and we need to find H4, which should not be difficult because we know T4 equal to 240, T4 equal to 1 bar. So again, we need to go to the tables. I mean, we can probably find the state here, 1 bar. What is the saturation temperature? 99.63, no? So really we know that it's superheated, correct? So we know table A4 at 240, how lucky we are that they have it here. So at 241 bar, we have the H will be equal to 2,954.5, okay? So table A4. We have that H4 equal to 2,954.5. All right, so finally we can say that the power of the turbine 2 will be equal to 18.77 times 3,899.92 minus 2,954.5. And this should be in kilowatts. And hopefully we should get something close to watts. 17 point, okay, no, so whatever, 1.772 to the 4 kilowatts. Do we get exactly that or do we get something different?
1.774, 1.775.
1.775, 4? Okay. 5, 10 to the 4? Oh, I didn't put, okay, so I don't know, whatever. Is that correct or it's not? Okay. So basically, I'm just putting what you give me here, 1.775, 10 to the 4 kilowatts. So we went and picked the longest one, no? Probably, no? But I mean, it's a good exercise. You practice the tables and all that stuff. So